Hello and welcome to Mathematics with Simon. I'm Simon. Today we're going to look at the A-level mathematics subject of sequences. So there are all sorts of sequences in mathematics. Here are some examples: the counting numbers, the even numbers, the square numbers, the triangular numbers and the primes. Sequences can actually be finite or infinite. All of these are infinite, but it could easily be finite. It could easily stop after a certain number. They also kind of come in four flavours: increasing, decreasing, periodic and constant. So in this case, these are all increasing, but you could have a decreasing sequence that might go like 1, a half, a quarter, an eighth. You could have a periodic sequence that might go like 0, 1, 2, 0, 1, 2, 0, 1, 2, or a constant sequence that would just go 3, 3, 3, 3, 3, 3. Interestingly, there are some sequences that are different from all of those four flavours. For instance, if you took the digits of pi and took those digits one by one as a sequence, they'd not be increasing, they'd be kind of random in some sense, although I'm not sure they're random because they are the digits of pi discussed. That's a very interesting topic actually. So we write these as follows: U1, U2, U3, U4, U5. That's the kind of notation we use. And so in general terms, what we would write is, for the counting numbers, we'd write UN equals N, because for instance the fifth term is 5, the seventh term is 7. For the even numbers, UN is 2 times n. So let's say the fifth term is 2 times 5, yeah, that's 10. Or the seventh term is 2 times 7, that's 14. For the square numbers, UN equals n squared. For the triangular numbers, UN equals n plus 1 over 2. And it's quite interesting to satisfy yourself that that's happening. Let's just try the fourth term, which is 10. Put in 4 here, you get 4 times 5 over 2. Which is 20 over 2, which is 10. And there is no general term for the prime numbers. Basically, they don't have a general term. It's one of the joys of the prime numbers. We can also write things as a recurrence relation. So in the case of the counting numbers, the term n plus 1 is just the previous term plus 1. Every counting number is just one bigger than the one before it. So UN plus 1 equals UN plus 1. For the even numbers, every term is 2 bigger than the one before it. So UN plus 1 equals UN plus 2. For the square numbers, every term is the one before plus 2n plus 1. And we set U1 equal to 1. And I've actually got some little diagrams to show this. It's fascinating. So this is 1 squared. Go to 2 squared, you add 3. Go to 3 squared, you add 5. Go to 4 squared, you add 7. Go to 5 squared, you add 9, and so on. It's really pretty. So in each case, you add an increasingly big odd number to get the next square number. There are some other kinds of sequence. So you get, if you keep adding a constant number, so UN plus 1 equals UN plus 4, and let's say U1 equals 3, you've got to specify the first term if you're going to do it as a recurrence relation. Then you get like 3, 7, 11, 15, 19, 23. You're always increasing by the same amount. These are called arithmetic progressions. So in this case, UN would be 3 plus 4 times n minus 1. So these are arithmetic progressions. And then you get another kind when UN plus 1 equals, say, 5 times UN. So you keep multiplying by the same number. So let's say you start at 2. So U1 equals 2, multiplied by 5 gets to 10, multiplied by 5 gets to 50, multiplied by 5 gets to 250. So in this case, you'd say UN equals 2 times 5 to the power n minus 1. So for instance, let's look at the third term. You go 2 times 5 to the 2. 2 times 25 is 50. It works. Arithmetic progressions and geometric progressions. Arithmetic progressions, you always add the same number as you move up. Geometric progressions, you always multiply by the same number, and we're going to do more on these in future videos. I hope you liked this video. I liked making it. You're very welcome to subscribe and the notification bell. I'd love to hear your ideas, and most of all, I very much hope you enjoy your mathematics.